Imagine you're at a crossroads in a forest, and you need to decide which path to take. Each path represents a different decision, and each decision leads to a different outcome. A decision tree is like a map of these paths. At each intersection or node, you evaluate a choice based on certain conditions, like whether it's raining or sunny. As you follow the paths based on these conditions, you eventually reach a final destination or leaf, which is the result of all the decisions you made. This structure helps you visualize and choose the best path based on various factors, just like how a decision tree helps in making choices based on different conditions. In this module, we will create a decision tree class from scratch using only numpy. The prerequisite for this module is having a basic knowledge of Python, understanding the concept of object-oriented programming, knowledge of the numpy library, and some machine learning concepts. The first step would be to divide the given dataset based on two criteria. The first is to get a feature index, and the second is the threshold value. A feature index is the feature of a given dataset that has high importance compared to other features. In simple words, it decides whether to split the data based on certain conditions. Now, let's imagine that we have identified the important feature index of the given data. Our next question would be how to split the data. To split the data, we need another variable called the threshold. The threshold value divides the data into two sets. For example, in a 5x3 dataset with 3 features, and the fourth column will be our labels. If we identify that feature index 2 has high information, we would use the second feature to determine the corresponding threshold value for each instance. If the threshold value is 4, then all instances smaller than or equal to 4 will go to the left node of the tree. Here, the tree is the actual decision tree with the root being the complete dataset. Similarly, instances greater than 4 will go to the right node. This process will repeat recursively. For the right node, we will again find a feature label and its corresponding threshold value to split the data. Recursion can be stopped either by using a hyperparameter called maxDepth, which limits the tree's depth, or by having a single instance after division. If you don't understand the concept of hyperparameters, don't worry, we will hard code it in Google Colab. So after seeing all this, we can say that a data can be split based on feature index and threshold value, which pushes us forward to our next task, which is to get the precise value of these variables. To get a good value of feature index and threshold, we calculate Gini impurity for each node in our tree. Gini impurity is the loss function for our decision tree model. The lower the value of Gini impurity, the better and stable the decision tree is. Let's understand it with an analogy. Say we have a bag containing 3 red balls, 2 blue balls, and 1 green ball. Then the Gini impurity of this bag will tell us how random the colors are. If all the balls were of the same color, then there is no randomness and the Gini impurity is 0. Whereas if all the balls are of different colors, then the Gini impurity is 1. Now to calculate the Gini impurity, we calculate the probability of all the colors, squaring it individually and then adding it. The resultant is then subtracted by 1, which gives 0.61 value. Similarly, we can do this for the other 2 bags. Notice how the last bag is not equal to 1 even if all the balls are of different colors. If we take 4 different colors, the Gini impurity will be 0.75. In other words, the greater the number of classes, the larger the Gini value. Gini impurity reaches its theoretical maximum when we consider an infinite number of classes with an infinitesimal probability, but in practical finite scenarios, it doesn't reach 1. In other words, it can never be exactly 1. The general formula can be written like this, which is the same as we did earlier. Now, why we will use this Gini impurity for our decision tree? Well, our goal in a decision tree is to split the data as long as each instance will fit into certain classes. Just like in the previous representation of our splitting dataset, the leaf nodes had different labels. If we calculate the Gini impurity of these leaf nodes, it will be obviously 0 since all the instances are of the same class. Meanwhile, the internal nodes and root node will have some Gini impurity. So our goal is shifted to reduce this Gini impurity by getting a good value of feature index and threshold value, which we will see in action in Google Colab. Before we get into the code, first, let's see the methods that we are going to use in the decision trees code. First, we define our class named decision tree. Here we will create a constructor with the init method, which will initialize our newly created object. The parameters here are max depth, which is the maximum depth of our tree that we want, and the other is minimum sample split. This split ensures that after some certain splits in the tree, it will stop, which will help to reduce the overfitting. We will come back again to this. The next method is fit method, which will fit, or I would say train the model with inputs given by user, but we will see fit method in the last sections. Since this fit method will take help of another method, which is the underscore grow tree method, the underscore here means that this method will only be used inside the class, not outside. It's a good practice to write these methods like this. This grow tree method creates the tree with the help of a dictionary. Just like we said earlier, the creation of a tree requires feature index and threshold. So this method also wants these variables, but we are not going to pass the values directly. Instead, we are just passing the input, labels, and the max depth of the tree. Don't worry about this default value of this max depth being 0. We will come back to this later. Next, we have the underscore split method, which takes inputs, labels, feature index, and threshold to split the given data into 2 nodes. The next method is the underscore best split method here. The actual calculation of Gini impurity and finding the best values of feature index and threshold occurs. This method takes time as it traverses through each feature and each instance to find best values of feature index and threshold. Once we find it with minimum Gini impurity, we return these 2 values. And the last 2 methods are the underscore predict and only predict method. The predict method will use the underscore predict method, so let's not talk about this further. The underscore predict method takes the input and the trained model's tree through which it traverses to get the required node, which we will see in action. So the overall working of the code is like this. First, we pass our input into the fit the method. The fit method will take the help of the underscore grow tree method to create the tree. The underscore best split method is used to find the necessary values of feature index and threshold of the current given data. Here I'm emphasizing the word current since the best fit finds threshold and feature index for each node's dataset, which will make much more sense when we will code it out. The split method will use these values to create left and right nodes, and then the grow tree method uses the underscore split method. This recursion will continue till we satisfy the maximum depth or have a single instance. And finally, we have the remaining 2 predict methods. Here we pass our input to the predict method, which further takes the help of underscore predict method. Now we will use our Google Colab to implement what we just learned. The link to this notebook will be in the description. You can also see the full code through this link of the GitHub repo. Like we said earlier, we will initialize the variables that we discussed. Notice here I initialized a variable named tree. This tree uses a dictionary to store the metadata of the current node. Metadata means the threshold value of the current node, the feature index, and its predicted value. Now we will see the underscore split method, which takes threshold and feature index to split the given data into 2 pieces. To explain the working of it, first we will import numpy as np alias. Here I made a small dataset with 5 instances and 4 features with y as labels containing classes 0 and 1. The feature index is 1 and the threshold is 4. X semicolon comma idx gives the instance's value of that feature. The smaller than equal to returns Boolean values, and the np.where returns those indexes whose values are smaller than 4. Here it's 0, 2, and 4. So we can find the exact indices where there are values smaller than or equal to 4 and greater than 4. We will store these indices in left and right variables, and the result will look like this. So the overall split method looks like this. Notice that this function returns 2 tuples, one for the left and the other for the right. Now let's look towards the best split method. Here we are going to find the threshold and the feature index. This function finds these variables until we find the node where Gini impurity is minimum. In other words, we will iterate through each feature and its corresponding instances and update the best Gini value till we reach the end. Let's see the working. So we're taking the same data set as previous one. Next, we will unpack the dimensions of the array. Here, n samples are 5 and n features are 4. We can use this np.unique method to find number of different classes present in dataset. In this case, it's 0 and 1. Now we will make a list comprehension. Here we traversing through the list of our different classes. And for each class's C, we find total number of occurrences of that particular class in Y label. And we are enclosing it in squared brackets to get the result in list. The result is 2, 3, which says that we have 2 instances with label 0 and 3 instances for label 1. The reason for doing is to calculate Gini impurity, since Gini is only interested in number of occurrences. In simple words, we can say that the dataset has 2 red balls and 3 green balls. And since we know total number of labels, it's easier for us to find Gini impurity through this. Here I'm storing this in numParent. Now to find Gini, we traverses through each element as I and divide it by m and then squaring it. This line is self-explanatory, so I will skip into this. For this dataset, our Gini impurity is 0.48. So now we know how to calculate Gini for a particular dataset. Now to get a valid feature index, we traverses starting from 0 to the number of features present in data. Say we are currently accessing the feature number 0. The corresponding instances look like this. Now we are zipping these instances with its corresponding labels. This will return a zip object. To access it, we will use a loop, and it will look like this. Now we will sort these based on the instances. And then we use asterisk to unpack the sorted elements and zipping it again. The result will give us 2 tuples. One are the instances of that feature in sorted order, and the other its corresponding labels. We do this for each features. Our objective to do this is to get the instances in sorted order, so that we know which instances are smaller than a certain threshold value and what are its corresponding labels. We will unpack the results in 2 variables. One is threshold and other is classes. Now a crucial step has come, so pay attention to this. We will create 2 variables. One is numLeft and the other is numRight. The numLeft is initialized with all zeros, which is the same as the size of numParent, whereas the numRight is initialized with a copy of the numParent. We will understand the reason for doing this once we go a little further. Now we start another loop to traverse through each value of the class's variable. The loop will start from 1 to the size of the number of samples. We are starting the loop from 1, which will be explained just after a few steps. The classes are these for the first feature. Say we have I equals to 1, then its corresponding class, which means the starting index, is this. We will store this value in C, and then we will increment the numRight at C position by 1 and decrement the numLeft by 1. We will visualize the working of this soon, so let's skip to the next step. The Gini left calculates the Gini of numLeft. In other words, numLeft acts like a bag of 2 different color of balls. For this case, we have 0 occurrence of 0 class and 1 occurrence of 1 class. Similarly, we can find Gini right for numRight. Notice for calculating Gini left, we are dividing it by I. In other words, if I will be 0, then it will result in infinite value. Therefore, we started the loop from 1. Also for Gini right, the denominator is subtracted by m, which will be explained once we complete this best split function. Once we get the 2 Ginis for left and right, we will find the weighted average of it. Then we update the best Gini value with the Gini if it is smaller it. Also, we will update the best t, which is the threshold with average of 2 thresholds, and then the best IDX, which is the feature index, is updated. And finally, after completion of loop, we will return these. Here we are taking the same dataset to find feature index and threshold. The feature index that we are accessing first is 0, and the I value is 1. We will iterate through the classes variable and see its corresponding threshold. The threshold and classes for this feature are created using the same method of sorting and zipping. The first element of the class is 0, and its corresponding threshold is also 0. So in the dataset, this is the location where the threshold is 0 with label 0. The numLeft will act like a container containing 1 0th class, whereas the numRight will have 1 0th and 3 1th classes. This value is generated by incrementing the numLeft and decrementing the numRight. After that, we will find the Gini of both the num and get the average weight of it. In this case, the average weighted Gini is 0.3, but we want the minimum possible value for all the instances. So we will iterate through the next class. Here the Gini is 0, and it makes sense since each num left and num right has the same number of classes. So this is the best lowest Gini for this data set. But for the sake of completeness, we iterate through each feature index with its corresponding classes till we reach the end. Once we reach the end, the minimum possible value for Gini is 0. We will find the average of its corresponding threshold values. In this case, it's 2 and 3. The reason for doing this is to reduce overfitting of the data. So the best threshold value is 2.5, and the feature index is 0. On the left-hand side, you can see the data, which is split using the underscore split method. Now back to Google Colab. This is the actual best fit method. Everything that we discussed so far has been implemented here, except 2 things. One is to return none when there is only a single instance or smaller than that. This is obvious since the best split works with at least 2 instances. Smaller than that will not make much sense. The second is to check if threshold I and threshold I1 are equal. Since splitting at either of these values would result in the same partition of the data, there is no need to evaluate the Gini impurity for the same split point multiple times, as it would yield the same result. After that, we will return the results. If we pass our dataset to this function, then the result would be the same that we yielded earlier. Next method is the grow tree method, which creates the tree recursively. Here, the inputs are the data plus an additional parameter called depth, with default value as 0. Here first, we will get the list of number of occurrences of a particular label present in data as num samples per class. Then, we use the argmax, which returns the index with maximum value. In our data set, it would be 1 since it appeared 3 times, while 0 appeared 2 times. Then we create a dictionary with key as predicted and value as the argmax that we found. This will create the root of the node with its first metadata as predicted. Next, a conditional statement where we compare if depth is smaller than the max depth that we initiated. The max depth default value is 2 and the depth is 0, so the condition didn't fail. Next, we get the IDX and threshold for the dataset that we have. Also, we check if IDX is not none. Since if it's none, then that means there is only one instance present in the dataset, which cannot be split further. Since it's not none, we get the left and right dataset based on IDX and threshold using the split function. Next, we are checking another condition if the length of the dataset is larger than the minimum sample split that we initialized in the constructor. This is to ensure overfitting of the data. Since if further split will happen, the model will learn complex patterns. Hence, we check if both left and right after splitting are of limited size. Next, we create new key value pairs containing feature index and threshold for the node, which is the metadata of the current node. Whereas the left and right call the function recursively, resulting in a creation of a tree. And notice that in the left, the function's argument is the x left and y left, which is generated after splitting, and similarly for the right. This is obvious since we want the left dataset for the late node and right dataset for the right. Also, the depth value is incremented by 1. If it is not incremented, then the function will be called recursively infinitely. By increasing depth at some point, it will be greater than max depth, which will be our stopping case for the recursion. Once this happens, we will return our node. Next, we have a fit method which stores the value returned by the grow tree in the tree, which we initialized in the constructor. After that, we have an underscore predict method, which takes inputs as a vector, not a matrix, remember. Therefore, the x here is small, not capital. Also, we take a tree which is trained. Inside the function, we are checking if the tree has metadata called threshold. If doesn't have one, which means it is not split further, so we will return the predicted data of the node only. But if threshold is present, then we get the feature of the input data. The feature should be the feature index present in that node of the tree, and we check if that value is smaller than or equal to the threshold. If it is, then we recursively called the function with the tree's left node as parameter, else do it for the tree right node. Once we reach the end, the else statement will return the predicted value of tree. After that, we can use the predict method, which takes inputs as a matrix this time, hence capital X, and returns the list of array for each instance which needs to be predicted using the underscore predict method. Hence, the overall code for the decision tree will look like this. All the methods that we discussed are used here. Now in the next part, we will see how to debug this code and create an advanced version of this. It's time to improve and fix our code. The first problem with our decision tree code is, what if our labels are 0, 1, and 3? When we use num left and num right, it will increment element at position 3, but we have the size of 2, which is a problem. In other words, we have to map the indices with its labels. For example, if we have 0, 1, and 3, then we will create a dictionary whose keys are 0, 1, and 2, and its values are 0, 1, and 3. Now we will highlight the changes that I made in the decision tree to fix this bug. First, we will initialize the class mapping variable, which will store the dictionary. In the best fit method, we will change the num parent variable. Here we will use classes mapping .keys instead of np.unique, since we want to access the keys, not the actual labels, because labels are not consecutive. Similarly, we will do that same for the grow tree method. We write class mapping .keys instead of np.unique. Now in the fit method, we will create the dictionary using dictionary comprehension. We use enumerate to get the label's corresponding index, and the key is the IDX and value is C. The rest of the code is same. We will create an instance of decision tree as model with max depth as 2 and minimum sample split as 2. We will fit our small dataset that we created and print the accuracy of the result. Here it's 97.3 since the dataset was too small. Even if we tweak the hyperparameters, it won't go above 97. The next hyperparameter we're going to add is minimum impurity decrease. This ensures the overfitting of the data, and it is quite easy to implement. First is to initialize the hyperparameter with a default value, and the second change is in if condition to ensure the difference of best Gini with current Gini greater than equal to with our hyperparameter. The next method we are going to add is predict probability method. This will return the probabilities of the classes that a given input belongs to. In the grow tree method, we will create another metadata named probability, which will store the probability of the current node. Here, the probability is calculated using the list comprehension and traversing through each element of the num samples per class. It is then divided by its sum, since the addition results in the total number of instances present in the data. Next, we will create underscore predict probability method, which is similar to the underscore predict method. The only difference is we are returning the probability metadata. Here in the function, it's vector. Next, we create predict probability method, and here we check the dimension of the input. If it's one dimension, then simply return it using underscore predict method. Else we iterate through each instance and predicts its corresponding values. Now to test this decision tree, we will import the iris dataset from scikit-learn and use train test split to split the given dataset, and we use accuracy as a metrics. After loading the data and splitting it, we will create a tree instance and fit our model with the dataset. We will predict the values using predict method and check the accuracy. Here it's 100%, which is very good results. And then we will use our newly created predict probability method to check for the vector at 50th location. Here the result says that the model is sure that this instance belongs to first class with 97%. We can add few more features to this code. For example, to visualize the decision tree boundaries, we can use matplot library. Second is feature importances, which is implemented in the GitHub repo. And the third is to visualize the tree. The result will be in PNG format. We can add more features depending upon the complexity of our problem. This code is suitable for classification problem. For regression problem, there is only few changes needed in this code. For example, instead of using Gini impurity, we will use mean squared error for calculation of loss. Now, in the future video, we will implement support vector machines from scratch.